All right, so in the final section of the gases chapter, we're going to look at the kinetic molecular theory and a few other things about how the gas molecules themselves are actually moving around. But we can use the kinetic molecular theory to essentially just describe gas samples. Whoops, that's not what I want. And if we look at it, we'll have a set of rules here. So the first one, gases consist of large numbers of molecules that are in continuous random motion. Two, the combined volume of all molecules of the gases is negligible relative to the total volume in which the gas is contained. Three, attractive and repulsive forces between gas molecules are negligible. So if we take all three of these rules to start here, essentially what it's just saying, if we think about a substance, any substance as it goes from solid to liquid to gas, what we're going to be doing is heating that substance up. So we're going to have the molecules or the atoms, whatever it's going to be for that particular one, are going to become more and more separated. And then when we finally get them into the gas state, they're going to be completely independent of each other. And that's what we're looking at for the attractive and repulsive forces. So once they're in the gas state, those gas molecules are essentially doing just whatever they want, independent of one another. They're just moving around randomly. And then when we look at the volume of that gas sample, the volume of the entire sample is going to be much, much larger than the volume of the molecules themselves. So if we took those molecules and then condense them back down to a solid, that volume is going to be much smaller than the volume that the gas is actually taking up, is essentially what we're saying with the second one here. And then with the last two, looking at energy, energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time, assuming that the temperature is going to be constant. And with that, if energy, if the kinetic energy is staying the same the entire time, what that means is the collisions themselves are going to be perfectly elastic. Otherwise, some of the energy would be lost just in the form of heat and things like that when they collide. But again, this is going to be at constant temperature, because if we heat them up or cool them down, as we'll see with the next rule here, we're going to see that the kinetic energy is going to change then. So the temperature is essentially just a measure of that average kinetic energy. So as the temperature goes up, the average kinetic energy of those gas molecules are going to increase, or as the temperature goes down, we'll see just the opposite there. And then this is basically just saying that exact same thing. So if we look at a graph here, what we have is each of these lines just represents a gas sample, the same gas sample at different temperatures. So blue is going to be 0 degrees Celsius, red going to be 100 degrees. And what we'll see is the average molecular speed, that's what we're showing with the dotted lines, is going to increase there because we're seeing the temperature increase. So the average kinetic energy is going to increase as well. And with average kinetic energy, we can just think of 1/2 mass times velocity squared. So if we've got the temperature higher, we've got the kinetic energy higher as a result, we'll see the average speed of those gas molecules is going to increase, assuming that it's the same gas. And with it, you'll notice it's not a perfect sort of central part of the bell curve here, just because it's not going to be a perfect bell curve. You can see at the higher end, it starts to tail off a little bit rather than just having sort of the same curve we have at the beginning here. And that's why we see the average kinetic energy, or the average speed rather, is just a little bit past where the kind of halfway point would be assumed to be. Oops, excuse me. So if we look at this one, not going to have to do any calculations, but we can just think through a couple different sort of scenarios or questions here. Assuming we have a gas sample, so just oxygen, for instance, doesn't really matter what it's going to be. But we have some sample that's initially at STP, so it's going to be 1 atmosphere of pressure and 0 degrees Celsius, or 273.15 degrees Kelvin. So standard temperature and pressure. And then we take that gas sample, compress it to a smaller volume while keeping the temperature constant. And then we want to think about how that's going to affect these other things. So with the first one, the average kinetic energy of O2 molecules and B, the average speed of those oxygen molecules. And what we're going to see, since the temperature is going to remain constant, doesn't really matter that the pressure is going to be increasing. But since the temperature is remaining constant for the same gas sample, we're going to see that those two are both going to stay constant themselves. But now if we look at the third and fourth scenario or questions, the total number of collisions of oxygen molecules with container walls in a unit time. So just how often are those gas molecules going to be hitting the container wall? We're going to see that's going to increase just because we haven't changed anything about the gas particles themselves. Essentially, we've just sort of tightened them up, put them closer together, so we're going to have more of those collisions. And the same thing with the unit area of the container wall per unit time. We're still going to see more of those collisions just because we've tightened everything up there. And then with this kinetic molecular theory, we also have what's known as the root mean squared speed of these gas molecules. And it's essentially going to be related to just the velocity. So you can see here similar things. But with it, you'll see at constant temperature, we see the average velocity. So if we just think about kind of the midpoint on each of these gases, we see the midpoint moving further to the right. And if we look at what these gases are, we've got hydrogen, H2, going to have a molar mass of about 2 grams per mole. Helium, 4 grams per mole. Diatomic nitrogen and oxygen are then going to be 28 and 32 grams per mole. So we see as these gases get heavier, or as they get lighter, I guess if we're going to the right-hand side here, as they get lighter, we're seeing the average velocity increase at a given temperature, just because the average kinetic energy is going to be the same. So again, if we think of kinetic energy, 1/2 mass times velocity squared, we're going to see that as the mass goes down, then the velocity is going to have to increase if we're keeping kinetic energy the same. And then if we look at the bottom graph here, now we're looking at just one gas sample. So we could have any gas since it's not really specific. But we're just going to have one single gas, and we're going to have it at different temperatures here. So now what we're seeing is as the temperature increases from 300 to 1,000 to 2,000, we're increasing the kinetic energy, but the mass is going to stay the same. So that's why we see the velocity increase. And then the root mean squared speed of these molecules is just going to represent kind of that average speed almost. But with it, we'll have, as the equation shows, the square root of 3 times the gas constant times temperature over the molar mass. As it says here, we want the molar mass to be in kilograms per mole. So typically we have that in grams per mole. We're going to change it to kilograms. And then with R, we're going to have that be 8.314. And then the units on that are going to be joule over mole Kelvin. And then the reason this is going to work, the reason we'll ultimately wind up with meters per second on the left-hand side here, is because when we plug in joules per mole, joule is really a kilogram meter squared per second squared. So we'll have the kilograms cancel with the molar mass kilograms. We'll have the mole cancel the molar mass mole. So kilograms per mole is going to get canceled out by the kilogram that's actually in joule, the mole that's just right here. Temperature, those kelvins are going to cancel. So the only thing we'll be left with is meter squared on top, second squared on the bottom. And that's why we're taking the square root of it to get to meter per second. So when we're looking at the root mean squared speed of these gases, we want to remember temperature, just like with pretty much every calculation with gases. We want to make sure that's in Kelvin. But then in this case, with the gas constant, we're going to want to use 8.314 joules per mole Kelvin rather than the 0.08206 liter atmosphere mole Kelvin. So if we look at the example here, and if you want to practice with this one, just pause it as always, but it's going to be using just that same equation. So what we want to consider, if I can get the drawing, the temperature, we'd really want 298.15 Kelvin. And then with the molar mass, remember, we just want that in kilograms per mole. So we would have, instead of 28.02 grams per mole, we'd have 0.02802. And then when you do that, you plug it all in, we'll have 3 times 8.314 kilograms per mole on top. So I'm not going to put it in the units here just to make it easier with the writing. But again, we'll have the R constant in joules per mole Kelvin, so we'll have 8.314. The temperature, we'll have the 298.15 Kelvin. And then on the, and then on the bottom, like I said, we'll have 0.0, because it's going to be diatomic nitrogen, so we'll double the nitrogen. But since we've got it in kilograms per mole, we'll have the 0.0208 number on the bottom, and then we'll take the square root of that. And what you should get is, we're paying attention to sig figs since we've only got 2 sig figs in that temperature. We would round this up to 520. And then if we look at some movement of gas particles, what some sort of processes that can occur are, effusion is going to be one of them, and then we'll see diffusion on the next one. But with effusion, we're looking at a gas essentially just escaping through a tiny hole. So if you think about just a balloon, eventually over time it's going to go flat, it's going to get deflated, because what's going to be happening is the gas molecules on the inside are going to be moving around, constantly hitting the container wall. But every once in a while, they'll find a hole in that container. And then as you can see with these two at the bottom, they'll just escape from there. And then we'll see, depending on the size of those molecules, so based on the molar mass, we can determine the rate at which that's going to occur. But similarly with diffusion, we're going to be looking at the movement of a gas. But in this case, we're going to be looking at kind of how it spreads out, rather than just trying to have it effuse through a hole. But either way, if we're looking at the rates of these processes, so again, effusion is essentially escaping through the hole in the container, tiny hole in the container. Diffusion is going to be looking at just sort of spreading out through a larger area. But either way, we can calculate the rates of these by looking at the molar mass. So we can compare the rate of effusion or rate of diffusion for 2 gases. R1 and R2 are going to be the rates, so gas 1 and gas 2. And then on the opposite side, we'll have the square root of the molar masses of those substances, but we'll have them inverted. So we've got the molar mass of the second one over the molar mass of the first one. And with this one, it doesn't actually matter what the units are. So with the root mean squared, we wanted molar mass in kilograms per mole. In this case, it doesn't matter as long as we've got the same thing on both sides. So as long as we've got kilogram per mole on the top and the bottom, or gram per mole on both of them, those units are ultimately going to cancel. So it's not going to be important what they are. But what is going to be important is that we've just got it set up in the correct way. So we're going to have the pieces of information for the same gas, just in opposite spots. So we've got M2 on the top here, R2 on the bottom on the other side, and just the opposite for gas 1. So if we look at the list of gases we're given here, and we're assuming at the same temperature, we want to figure out the rate of diffusion. Would be the same thing for effusion, but for these different gas samples. And again, the rate is going to decrease as the molar mass increases. So we would just want to see what the molar masses of these different substances are. And we're going to see hydrogen is just about 2, carbon dioxide 44, argon just under 40, sulfur hexafluoride is going to be 146, uranium hexafluoride would be 352, and krypton would be about 84. So if we have one being the fastest, we'll have hydrogen, then we'll have argon, carbon dioxide, krypton, the sulfur compound, and then the uranium compound. And again, this is just based on the molar mass. The smaller that molar mass, the faster the rate of diffusion. So that's why hydrogen is the fastest. Uranium, the uranium compound would then be the slowest. And then a unknown gas composed of homonuclear diatomic molecules effuses at a rate that is only 0.355 times that of oxygen at the same temperature. Calculate the molar mass of the unknown, and then determine its identity. So the determine its identity part may seem a little bit challenging, but since we're told it's a homonuclear diatomic molecule, we just think about what that means. Diatomic means we'll have two of those atoms. And then homonuclear means the nucleus of both of those atoms is going to be the same. So we're going to have just some diatomic molecules. So it could be hydrogen, oxygen, nitrogen, any of the halogens, basically. But in order to identify it, we'll need to get the molar mass first. And with it, we can use that rate equation, where the rate of the unknown gas is 0.355 of oxygen. So I'm just going to put 0.355 on top. And then oxygen would just be 1. So we can place that on the bottom. And then on the opposite side, we'll have the square root of the molar masses just in the inverted order. So we'll have 32 for oxygen, 32 grams per mole. We could do kilograms per mole, but wouldn't actually matter because the units on the bottom would just cancel it. Oops, that X came out terrible. There. So again, we just switch around the molar mass with the rate. So that's why we've got the pieces for oxygen on the bottom on the left, the top on the right. And then what we can do is just square both sides. And then cross multiply, divide by the factor on the left. And what we're going to see is that the molar mass of that unknown substance is going to wind up being 254 grams per mole. So what we need to then do is look at our periodic table, and again, since we're told homonuclear diatomic molecule, we know it's going to just be two of the exact same element. So we need to find something that's got an atomic mass of half of 254, which is going to be 127, which is then just going to be iodine 127. And we'll see that the identity of that gas molecule then is just going to be I2. And with it, we can just think about what we're plugging in here, because now we've got a much larger gas molecule compared to the oxygen, 254 compared to 32. So that gas molecule, the larger one, is going to diffuse or effuse, either way. It's going to go through that process much more slowly, and that's why we see the rate is going to be about 1/3 of what we have with the oxygen. Oops. Clear all that. Okay. And then up to this point, we've essentially been treating every gas sample as an ideal sample, ideal gas. And that's what we can use the kinetic molecular theory to kind of describe as that ideal gas behavior. But in reality, the gases we're going to deal with aren't going to behave in that way. Especially if we don't have them at high temperature and low pressure. So if we just think about solid versus liquid versus gas, as we go from solid to liquid to gas, the way we do that is either heat up the sample or decrease the pressure, because either way we're going to allow those molecules to then separate, to spread out, and then with the gases we just have them fully independent. But what we're going to see is if we don't have a gas sample at high temperature and low pressure, we're going to see pretty large deviations from that ideal behavior. So if you look at the graph here on the y-axis, we've got PV over RT. So if we had ideal behavior, everything would just be on this one line going across here. But as the pressure changes, we're seeing deviate, or as the pressure increases, I should say, we see deviations from that ideal behavior. And we see extremely large deviations in the cases of high pressure, so where we're forcing those gas molecules to be closer and closer together, or if we've got low temperature, or if we've got the combination of both. Because again, with the low temperature, now we're going to be slowing down those gas molecules. The pressure or the volume that they're going to occupy would decrease if we keep the pressure constant. But we're just going to be essentially slowing those down and decreasing that ideal behavior, because now we'll have a little bit more interaction between those gas molecules. The collisions are going to be less elastic, and like I said, we'll just have less of that ideal behavior. So when we're looking at the gas law, there are actually corrections for the gas law known as the van der Waals equation. So you can see we still have kind of the same pieces, pressure and volume on the same side, and we're going to be multiplying those together. Moles, gas constant, and temperature on the other. But now with the van der Waals version of this equation, now we've got these correction factors in here, A and B, the square of the volume on the bottom here. And this is going to account for those deviations from the ideal behavior. And then depending on what gas it is specifically, A and B just refer to constants, but depending on the gas itself, we've got different values for those, because the real behavior of these gases will be different from one another. But for the purposes of this course, we'll only be focusing on the ideal behavior. This would be something that more comes into play in a physical chemistry course. But just so you can see it, with real gases, there will be deviations from that ideal behavior.